Good afternoon to everyone. So we are delighted today to have with us one of the most world-renowned meteorologists. So with 4 decades of experience working in the climate and meteorology field. So his talk, as you can see, is going to talk about the Indian monsoon, the dynamics, variability, and prediction. And I was talking to Sir today, and then as I was trying to understand his career graph, so he seems to actually work across India, started his career in TIFR, and then all the way to his illustrious career through IITM, ISRO, and Ministry of Earth Sciences as secretary, and currently he is leading the Atria University as the vice chancellor. So he's renowned for his contribution to developing daily meteorological data for India and his contribution to understand the extreme events across India like weather, which helps the country to actually prepare better for the unseen or the uncertain picture that we actually face because of climate change. Having said that, I would like to invite Professor Rajeevan sir. So please come and yeah.
So thank you very much, Harini, Sandanu, and Premji University for inviting me to give this visit and give this presentation. So next 1 hour or so, I will be talking about the basic dynamics of monsoon. What is monsoon? How it happens? Why it happens? And how monsoon varies with different time scales, and how we predict monsoons. So you can interrupt me and ask questions in between if you really want. Otherwise, I'll just go through it. Yeah, this is the outline of my presentation. So I'll talk starting from basics, then mean monsoon and variability, how we predict monsoon, what is the present skill of monsoon forecast on different time scales, and what we should do to improve the monsoon forecast. And probably this new technology is coming out is AML. So whether the prospect of AML methods in improving monsoon predictions. And if you really ask a question how the monsoon has really originated, so I'm not an expert in this, but then I thought I will start from here. So there was a continental drift. India was a part of the Antarctica. Australia also was a part of Antarctica. Many million years ago, they started moving. It's called continental drift. It did not happen in an overnight. It happened in a small time scale. It's at rate of about 9 to 16 centimeter per year. And so this was India somewhere 70 million years ago. It was somewhere here. Then 50 million years ago. Then it started colliding with the Eurasian subcontinent. So that's why the Himalayas started growing up afterwards when these two continental continents were shifted, colliding each other. The Himalayas came, the Tibetan plateau has come. So that is the beginning of monsoon. So monsoon, for beginning of origin of monsoon, is almost 50 million years ago. And also the development of Himalaya, the uplift of Himalaya was one of the primary reasons for monsoons to have. And when we really talk about monsoon climate, we have records of observations for 150, 160 years, but you don't have real observations taken by a human being. It's not available in the earlier years, so we have called proxies, climate proxies. One climate proxy could be ice core. You can go to Antarctica, or if you're in India, you can go to the deep sea and take the ice core. And you can not ice core, but the cores, and then you can measure the how the monsoon was in terms of isotopes, oxygen isotope in 18. And also you go to caves and take the speleothem, or go to forest and cut the trees and see the measurements of how the tree was growing. So these are some of these proxies we call. And to some extent, the proxies are good. And you cannot accurately find out what the monsoon was, but then you can see how the monsoon was progressing or decreasing. So this is one isotope data for last 2000 years. You can see that some years monsoon was good. It's called mid-warming period, medieval warming period. Then you have less rainfall here. and before 200 years before, and this was ice age. So then we had less monsoon, we had a good monsoon here. So this is some of the reasons we have variability of monsoon in longer time scales. And at present we have two monsoons. One is southwest monsoons during June to September, and then we have northeast monsoon during October, November, December, but that is confined mainly in the southern parts of the country. So the question is how the monsoon really starts developing. So if you really, it's a simple physics. So in December, January, February, this is the distribution of temperature. The Indian subcontinent is cold, ocean is warm, Indian Ocean is warm. And you can see the temperature gradient is from here to here, from south to north. But when it comes May, June, July, Indian subcontinent and so-called the Arabian subcontinent gets heated up, and temperatures are much warmer, and ocean is cool. So temperature gradient is just reverse from north to south. Okay, and temperatures are very, very abnormally very high here, and also over the Arabian subcontinent. So what is the difference between these two seasons is the temperature gradient, reversal of temperature gradient. Once temperature gradient is all because sun comes into the northern hemisphere during May, June, July, it heats up the land surface much faster than ocean. The ocean has a larger heat capacity. So given a kind of energy input, it takes more time to heat it up. Whereas land gets heated up quickly. Okay, so land gets heated up quickly when compared to ocean. So this region is much warmer. So the temperature gradient reverses. When your temperature gradient reverses, surface pressure is nothing but the weight of the atmospheric column. And that also gets reduced. So it also gets reversed. You can see that during December, January, February, you have high pressure over here and low pressure here. So the pressure gradient is from here to here, north to south. Whereas in May, June, July, there is a low pressure here because temperatures are high. So the whole atmospheric column is less density, and less density means less pressure. So you have low pressure area here, and you have a high pressure here. So pressure gradient is from south to north. Okay. So if you have, atmosphere is nothing but a fluid. The fluid moves from a high pressure to low pressure. How water flows from a high pressure to low pressure. Similarly, atmosphere also flows from high pressure to low pressure. So in the May, June, July, August season, the summer season, the air comes from southern hemisphere, flows across the equator and comes to northern hemisphere. Then what happens means Earth is rotating. It's from west to east. So then we have a concept called Coriolis force because of the concept of Earth's rotation. Because of the Coriolis force, when the air comes from south to north, crossing the equator, it gets deflected towards right in the northern hemisphere. In southern hemisphere, it gets deflected towards left. So when otherwise the flow would have been simply south to north. Because of the rotation, it becomes southwesterly. So we call the summer monsoon also southwest monsoon because winds are southwesterly direction. So this is the wind flow during January. You can see it's all northeasterly. So that's why we get a northeasterly monsoon here. And when monsoon season during June to July, you get this. This is the cross-equatorial flow I'm talking about. You can see that it simply flows here and moves here. So this is, you get a strong westerly flow, southwesterly flow. This is monsoon circulation. And this is the high pressure cell in the southern hemisphere. From there, the outflow is simply the air flows out, comes here, cross the equator, and becomes southwesterly winds, and you get a monsoon flow. So that is the way. So the monsoon flow really starts from southern hemisphere. And over here, you can see that it just crosses across the equator, very close to the African coast. It's called Somali coast. So if you really see the vertical profile of the vertical extent of this cross-equatorial flow, it looks like this. May like this, June like this. It's a very narrow but very strong flow. So we call Somali jet. Jet means it's a strong winds. So this is a beautiful monsoon flow, cross-equatorial flow which happens. And slowly it gets reduced by October. And this is the southwesterly flow basically. This is strong winds. This is at 1.5 kilometer above sea level. And you get a strong cross-equatorial flow and monsoon flow. And so how you explain this circulation? So you must have heard about land-sea breeze. During daytime, land will be warmer and ocean will be colder. So land air will go up and descends over the ocean, and from ocean water flow will come here. Okay, so that is daytime. Night it just gets reversed. That's why the coastal regions, especially cities like Chennai and all, the temperature difference is not much. Well, they have sea breeze effect in the daytime. The nighttime just gets reversed. Whereas in Delhi and all, the sea breeze effect is not at all seen. Okay, so the sea breeze effect is very. So basically, sea breeze is nothing but air from hotter temperature, air goes up, sinks in over colder ocean, comes back. So it's kind of a vertical circulation. Okay, so many people in the beginning they thought monsoon also is a large, gigantic sea breeze. Okay, it comes from southern hemisphere, goes up to Indian longitude, Indian latitudes, and goes up because of the convection, then comes back and returns. So it's a large north-south kind of a gigantic sea breeze circulation. That was the hypothesis we had. So initial years, if you really see how you define monsoon, monsoon is nothing but a large sea breeze. Okay, so the theories which started from the earlier years, one is Halley. Halley is a very famous person. You must have heard about Halley. Halley is comet and all you must have heard about. It's a British astronomer. So he hypothesized that the main cause of the annual cycle of monsoon circulation was the differential heating between ocean and land, caused by the seasonal march of the sun. Then Halley, 1735, he told that airflow across the equator towards the warm landmass is turned to the right because of Earth's rotation, creating the southwesterly winds. So these two theories basically said that the land-sea temperature contrast is much more important for a monsoon circulation to set in. And without this land-sea temperature contrast, monsoon would not have been there. So that is true. So without monsoon temperature gradient, the air won't be moving north and going up, then coming back. But that theory is very simplistic theory. Later years, when we started analyzing monsoon variability, this theory cannot be really used for explaining the variability. It can explain the basic idea of how the monsoon is, but it cannot really explain how the monsoon variability happens. I'll give an example. This is a example of this is the Halley circulation we call. Air goes up, comes down, and goes up. It's called Halley circulation. In the monsoon region, air goes up in the Indian region, goes up 200 kilo. It's a pressure. It's about 16 kilometers. It comes down, and then again it comes back. So monsoon, they thought this is a gigantic sea breeze. But then this theory doesn't work. So if this is really true, if land sea temperature contrast is more, it should lead to a good monsoon. Yes or no? If land sea temperature contrast is a basic driving force for monsoon, if temperature contrast is more, then you should get a good monsoon. But if you really plot the temperature contrast and monsoon rainfall, it just reverse. So if more land sea temperature contrast doesn't mean that it's a good monsoon. So there's something is missing. Okay, so that theory is a basic idea. Land sea temperature contrast is good. It can explain how the monsoon starts, but it can't explain everything of monsoon. That's a basic thing. So how you explain? This is the explanation which the new theory says you can really calculate where the precipitation exceeds evaporation. This is the northern hemisphere where the precipitation exceeds evaporation, and this is all monsoon zone. Okay, in the southern hemisphere, this is all blue. So what we see is the next picture. We can see that this is the rainfall during January, and this is the rainfall during July. You can see that it's all from satellite observations. You can see there is a northward shift of this rainfall zone from the equator towards the Indian region here, and also over China and East Asia. And during January, that means our winter, but for southern hemisphere it is summer, so they have a shift of rainfall towards Australia. A similar shift is happening in Africa also. You can see that it is not there, rainfall is not there, but during July, there's a lot of rainfall activity. So this northward movement of ITC, we call intertropical convergence zone or rainfall zone, is the main driving force of monsoon. So if you have this concept, you can explain everything. So that can be seen even in satellite photo. This is nothing but ITC set. Intertropical convergence zone, where you get a lot of convergence of air, then air moves up, you get a lot of clouding, a lot of rain, and that moves north and south. And during monsoon, this is the way in July, January, this is the position of ITC and July, this is the position of ITC And you can see that it doesn't move very much throughout the globe. It moves only over in the African region, and it moves only over Asian region. And that's the driving force of monsoon. So wherever this ITC moves north, there is the monsoon happens. So monsoon is not there everywhere. Pacific, there is no monsoon. Okay, so the question is, where are these monsoons? This is the monsoon region. So we have a definition, it's a global concept. We have a definition of monsoon, where the local summer minus winter precipitation rate should exceed 2.5 millimeter per day, and the local summer precipitation exceeds 55% of the annual. If you really put the criteria, this is the South Asian monsoon, this is the East Asian monsoon, this is Australian monsoon, we have a North American monsoon, we have South American, we have South African monsoon, we have North African monsoon. Out of that, the South African monsoon, South American, North American monsoons are very weak system. It's not very prominent climate system, whereas South Asian is the most prominent climate system in the world, whole globe. And East Asia to some extent, and also North African monsoon. And Australia, for them, this is very important for them. Okay, so now how the rainfall distribution over India. So this is the rainfall from merged rainfall from rain gauges plus satellite observations. And you can see that beautiful rainfall pattern during June, July, August, September. We call climatology. And you can see the west coast gets a lot of rain, and also northeast gets a lot of rain. So rain over Rajasthan and all is much less compared to also the southeastern parts. But rainfall, heavy rainfall zone is here. So rainfall decreases from here to there. So this is the spatial distribution of monsoon rainfall. This is the coefficient of variation of same rainfall, but the coefficient of variation in terms of percentage. And if you really plot, if you take the Asian monsoon, the whole region, and plot the monthly graphs, this is the rainfall. It picks up in June, July, August, September, whereas the coefficient of variation decreases during this period. During monsoon season, it is about 10%, 10 to 15%. And now question is, in monsoon season, all the days it doesn't rain. It rains only on few days. And when the rain is there, we call it a rainy day. So in IMD defines a rainy day when the rainfall is 2.5 millimeter or more in a day, 24 hours. So if you really calculate the number of rainy days, this is a spatial distribution. It resembles very well with the total rainfall. We have 2.5 millimeter rainfall and more. And if you take a 65 millimeter or more in 24 hours, in IMD's definition of 65 millimeter more is called heavy rainfall. So this is the spatial distribution of heavy rainfall. You can see that where heavy rainfall occurs more is basically west coast, northeast, close to foothills of Himalayas, and whole central India. This is the region where you get maximum number of frequency of heavy rainfall events. Now question is very simple question. How many hours it rains? Out of 122 days into 24 hours in a particular station. You take any station in Bangalore. We know it doesn't rain all the days, it rains only few days. Those days are called rainy days. But even on a particular rainy day, it doesn't rain all 24 hours. It rains only few hours. Many of us doesn't know how many hours it rains. Even big people working on water management, agriculture farms, they doesn't know. So we did a work recently and found out how much the rainy hours is there. You can see that along the west coast, the rainy hours is about 500 hours, whereas in northwest India, it is hardly less than 100 hours. And here it is little more than between 300 and 400 hours. Whereas in Bangalore, it is less than 100 hours. So after 122 days, in 122 into 24 hours, it rains only less than 100 hours in a day. And you say the whole season. Very few hours it rains. So why I am telling this, and out of that, 50% of rainfall comes in these hours. Very small number. What really it means it rains in few hours, but when it rains very heavily. First few rains will be of very heavy intensity. Okay, it's of order of 50 millimeter, 60 millimeter, and that occurs in a few hours. Then remaining rainfall in 2 millimeter, 1 millimeter, 0.5 millimeter, that occurs in a longer time scale, longer hours. So that is very important. So when it rains very heavily in small hours, the whole rain, when it comes, it flows off. It's called runoff. That water is not available for water storage. It flows off. The remaining hours, it rains in a small number, 2 millimeter, 3 millimeter, and before it reaches the surface, it evaporates. So that is the basic driving ideology saying that you should conserve water. The whole rainwater harvesting, etc. Why we are talking it? Mainly because of this characteristics of rainfall. It rains only few hours everywhere. But when it rains very heavily. So that water, you please store it. Don't allow the water to flow. But be careful, during flooding happens, don't store it. Okay, when flooding happens, you allow the water to flow. But otherwise, please store the water. So there's a whole concept for rainwater harvesting. If in Tamil Nadu, I understand that in a city in Chennai, if you really want to have a society, housing society, rainwater harvesting is important. Otherwise, they will not give a license. So we should have this kind of policy. So I urge that all of you should follow the procedure of rainwater harvesting. Some people store it under the ground. Some people store it in water storage systems. Whatever you do it. But now the recent studies, we published a paper in last year, a few months back it's a natural journal, and journal published by Nature. And when we found out this number of total hours occurring in the first few hours, also the number of hours being taken is much reduced now. Instead of early days 20 hours, now it happens in 10 hours. That means the intensity of precipitation is increasing everywhere. This is a new concept which we are introducing. This is different kinds of cloud. What kind of clouds we have over the monsoon region? This can be taken from the satellite. So this is month of May, June, July. You can see that during June, monsoon comes, the whole clouding is a total cloud fraction. It's about 70 to 80% clouds. Then slowly it gets reduced in October. Now, variability. Monsoon varies in different time scales, starting from diurnal. Diurnal means within 24 hours, monsoon varies. Okay, and synoptic means next to 3 to 4 days, 5 days, monsoon varies. Intra-seasonal, within season, there can be a few days you get more rain, few days you get less rainfall. It's called intra-seasonal activity. Then from year to year variation. 1 year it will be good monsoon, another year it will be a poor monsoon. So we have year to year monsoon. So there's intra-annual variability. And then longer time scales, decadal time scale, 30 years, 40-year time scales, also there is a decadal variability. So monsoon varies in different time scales. So we should really understand how it happens, why it happens, so that we can really start predicting it. This is a diurnal variation. I will focus on this map. This is basically you do a harmonic analysis of hourly rainfall data, and you get this kind of map. This map shows the time of Indian Standard Time in which you get maximum rainfall. Okay, so that is in the foothills of Himalayas. This is hours, Indian Standard Time. You see here the close to foothills are blue. That means the early hours. So foothills of Himalayas, they get maximum rainfall in the early hours of the day. Okay, it rains maybe raining remaining days, but the remaining hours. But maximum rains comes in the early morning. But whereas our central India and all, it's basically the late evening, 15, 18 hours. So there's a lot of variation in the diurnal variation in the country. And if you really plot the 3 hourly rainfall data, this in the early morning, 5:30, then 8:30, 11:30, then 14:30, 17:30, etc. You can see that large variation. In the early morning, you see the whole foothills of Himalayas are raining. Whereas over central India, not much rain. But by afternoon, you see that it starts raining, a lot of rain. And also along the west coast, also rainfall variation. In the early morning, there's a lot of rain. Slowly, it starts reducing it. This is called diurnal variation. So there's a lot of physics involved, right? I will not go in detail. The rain over here, the central India and the early convection, so afternoon convection is basically solar radiation. Solar radiation heats up the land, it's heated up, the air goes up with a lot of moisture and it gets rain. We call convection, local convection. Okay, so now on the synoptic time scale, we have low pressure system forming here, moving north. This is in June. This is July, August, September. So different months. You can see this is the track of low pressure system forming out. And we call those systems called monsoon depression. It gives maximum rainfall over the country. This is the main predominant weather system in the monsoon season. And this is the rainfall associated with that. Then in a particular day, 122 days you take, and you plot the rainfall activity over India, you get this kind of graphs. So some days there will be good rain, then some days less rain, then again good rain, some days less rain. If you plot the anomalies of a particular day, you get this kind of graph. There are days in which above normal rainfall, then days in which you get less rainfall, then again good rain. So this is called, we call active break cycle. So we have an active monsoon season, period, followed by a break, then active, then break, then active. So this is a very predominant phenomena in the monsoon season. So as I said, the question is, when it rains here, can we predict this will happen now in the next few days? Or when we are somewhere here, can we predict this will happen? Similarly, when this is there, can we predict this long weak spell or break spells will happen? And when you are here, the question is, farmers will really get fed up during this season, during this period in which there is not much rain. So they will wonder whether we can get this kind of spell for the next few days. So these are some tricky questions which we need to answer. This is the break spell, how the rainfall is. It will be, whole country will be without rain, except this region, northeast India. When the active spell happens, the whole country will get a lot of rain, but northeast India, foothills of Himalayas, southeast India will get less rain. This is the clouding associated with the break as well as is active. Break, you can see most of the clouding is over foothills of Himalayas. You get a lot of rain there. Where in the active spell, the whole country is covered by clouds. Okay, then the year-to-year variation. So if you really take the all India average of rainfall over monsoon season, it's about 87 centimeter. You take all the rainfall data over the country and take an average, arithmetic average, you get about 87 centimeter. 87 centimeter annual, if you take, it will be about 1100. It is 110 centimeter. What do you mean by 110 centimeter? It is little more than 1 meter. So how you interpret that 110 millimeter, 110 centimeters, 1 meter rain? The meaning is, if you assume that water, whatever it is coming as rain, doesn't flow out to the ocean, it also doesn't evaporate. At the end of 31st December, the whole country will have 1 meter of water. That's the meaning. Assume that there is no overflow, water doesn't flow. And you know how much area is. Multiply by the depth, 1 meter, you know how much volume of water we get. Still, at the end of the day, we say there's no water. So we are fortunate that we have good monsoon. We are very fortunate. I'll tell you frankly, if you did not have monsoon, you could have been some country like Somalia. You will be, instead of carrying your pen and book, you'll be carrying AK-47, pushing people. So that's not happening because we have monsoon. That's why I am interested in monsoon, because it's bread and butter for all of us. If monsoon was not there, we will not be like this. That's the meaning. So we have year-to-year variation monsoon. Some years it goes up, some years it comes down. And these red years are all we call drought years, where we have impact on agriculture, etc. There are years in which you have good monsoon. The question is why monsoon rainfall is very important. So there is a study by Gadgil and Sulojana Gadgil and her son. Sulojana Gadgil is wife of Madhav Gadgil. And so they had done a work on how the monsoon rainfall is related to Indian GDP. Okay, you see that it's a beautiful graph. It shows when monsoon rainfall is below normal, the GDP gets affected. But when monsoon rainfall is more, GDP also gets affected, but it's not appreciably big one like the negative rainfall. Okay, but there is a relationship between monsoon rainfall and India's GDP. It's very, very important. So monsoon rainfall really affects India's GDP. So a big drought year can pull down the Indian GDP at least by 2 to 3%. 2 to 3% of GDP is very big number. Okay, so that is where the importance of monsoon rainfall prediction comes. Whether can we predict in advance whether this rainfall will be below normal, above normal, and whether it will become drought. If it will become drought, it can really affect GDP. So Indian government has to take accordingly the precautionary measures, adaptation measures they have to take. So why monsoon varies? Because mainly it's influenced by Pacific Ocean, and also to some extent Atlantic Oceans and also Indian Ocean. So oceans play an important role in driving monsoon from year to year variability. This escape, and how we make predictions. So, and I have another half an hour? 25 minutes, good. So how we make predictions? So before that, I want to see I want to convey the meaning of difference between weather and climate. And climate is, climate is what you expect, but weather is what you get. Okay, so Bangalore may be good in climate, but on a particular day, the weather could be very nasty. It can heavy rain, flooding, everything can happen. Otherwise, Bangalore is a good city for climate. Similarly, Coimbatore, people say it's a good city for climate. Okay, so climate and weather, climate is nothing but a long-term average, but weather can be instantaneous weather, today's weather. Okay, so question is, so climate prediction is different from weather prediction. That's the meaning. Okay. Okay, so now for predicting weather, we have different atmospheric phenomena. For some, a dust devil, you can see in the summer, some air will be flowing and just taking the dust and moving. It's a small phenomena. Okay, that will be about 10 meter width scale. It occurs in minutes. And then you have cloud, then tornado, then mesocyclone, thunderstorm. Thunderstorm is about 50 to 60 kilometers size. It occurs in few hours. Sea breeze, precipitation. Tropical cyclone is about 1,000 kilometers, and the period is about few days. Then large scale monsoon circulation is about 10,000 kilometers. It is in months together. So the prediction also will depend upon for which you want to predict. You want to predict thunderstorm cloud, you want to predict tropical cyclone, you want to predict cumulus clouds, you want to predict dust devil. So depending upon which parameter you want to predict, the philosophy of prediction will differ. Okay, you cannot use the same kind of technique of predicting tropical cyclone to predict thunderstorm. Okay, because tropical cyclones have the larger spatial scale and time scale, whereas thunderstorm is a few hours. If thunderstorm happens in next 2 hours, you will not see, it will die. And the spatial scale is very small. So the strategy for predicting different weather systems will be different, but the concept will be same. So this is the different forecast we have. We call nowcast, then very short range, short to medium range, extended range, seasonal, annual to decadal. So we have then climate change projections. So when you talk about climate change, what will happen next 30 years, 50 years, then those things are not called prediction, we call projections. We don't call prediction. Prediction is, it has little more accuracy. Projection means we project, oh, this will happen. It's kind of a scenarios. Okay, so when we talk about climate change, we never talk about climate change prediction, we talk about climate change projections. So that we should understand the difference. And this I'll skip. And what kind of phenomena is involved in predicting weather? For example, if you want to predict minutes to days, only atmosphere is involved. Ocean is not becoming important because ocean is very sluggish. On a particular 2 days time scale, 3 days time scale, ocean doesn't change. Okay, because very sluggish, because heat capacity is more. Whereas land can change, for some temperature over land can change very quickly, but ocean temperature cannot change that so quickly. So ocean is not important for few days, a couple of days, 2-3 days. But when it becomes months together, for example, monsoon seasonal forecast, next season, then ocean will become very important. When you talk about 100 years, then deep ocean will become important. Sea ice will be important. For 1,000 years, sea ice sheets will be important. Biosphere. So depending upon when you want to predict, how many days you want to predict, you should use this kind of thing. So if you want to predict only weather, you need an atmospheric model for next few days. If you want to predict next 1 month, you need an ocean. So you need ocean plus atmosphere, two coupled model you need. If you want to predict on climate change time scale, you need deep ocean, you need sea ice. So depending upon the need of the forecast, you need the different kinds of model. And these are different kinds of models we use. And the first numerical weather prediction model, the mathematical model in which we use for prediction, started in somewhere in 1913 by a person called Richardson, 1922. He thought these mathematical equations can be solved. For that, you need, it's a pictorial imagination what he made. He thought it's all big company, big building in which many people will be sitting together and solving the equation. But then there was no computer, there was no concept of computing. So he thought that people will be involved. It's like a factory to make weather prediction. But his first prediction was very, very bad. He could not really do well. He could not really solve. The real breakthrough came in 1950 by a person called Charney. It's a very famous person. He was nominated for Nobel Prize for a couple of times, but he did not get. You must be, I don't know whether computer science people know him, Von John Neumann, who first developed the first computer in the in the whole world. And he solved this equation. It's a barotropic vorticity equation we call. It's the first time a weather prediction is made in 1950, 11 years before my birth. So it is almost 75 years now. So the first computer they used is called ENIAC computer. So it is becoming now 75 years old. This year it becomes 75 years old. And that is the computer is huge. It may be of this size, this room size. And if you really see the computational capacity, it may be even worse than your mobile. Worse than your mobile. But now we have best of best computers. It's called in petaflop time scale speed. And we have recently Ministry of Science upgraded their computer into 22 petaflop. That's the fastest computer available in this country, 22 petaflop. Petaflop means 10 power 15. So 22 petaflop speed means how you interpret is per second. So 22 into 15 times 0, arithmetic operations in 1 second. This is 1 second. So 1 second, 15 followed by 22 followed by 15 zeros, operations will be done in 1 second. So you can just imagine how much speed it is. And we use it, and we now know that this is not sufficient. Okay, so we are asking for much more better computing facilities. At present, we have 22 petaflop. Okay, so for that, for every forecast, you need a initial state we call. So we need actual observations of the day. So we have so many observations which comes up from satellites, we have ships, we have drifting boats, we have aircrafts, we send balloons, we have automatic weather stations, we have meteorological observation stations. All this data comes to one place. It is, and also it's shared with different countries. Our data goes to Pakistan, Pakistan data comes to us, our data goes to US, US data comes to us. So we exchange it on a real time mode, all this data. And because weather, the atmosphere doesn't know the boundaries, national boundaries. A weather system forming over Pakistan can form, it can come to India and it can rain. Similarly, Indian weather system can go there and it doesn't understand what is the political boundaries. Okay, so we need to share this data. So it is shared under an umbrella called World Meteorological Organization. It's like WHO, the World Health Organization. We have an organization called World Meteorological Organization in Geneva. Under that umbrella, we share all the data. So all this data comes to all the people. This is some kind of data. This is a surface observation. Where land is there, or oceans are ship observations, and we have a lot of satellite data, huge satellite observations we have. And this is the basic model equations we solve. This is nothing but very simple concept. Conservation of mass. Mass is conserved, we know. Mass cannot be changed. We know momentum is conserved. We cannot change the momentum, okay? We also know energy is conserved. And also there is a concept called hydrostatic balance. So all these basic physical laws, we put it into an equation, solve this equation, using the initial condition. Initial condition from where it comes from the observations. Okay. Then these are all nonlinear equations. You don't have an analytical solution to solve, to get an answer. So we adopt the empirical methods, numerical methods. One is finite difference method. I don't know how many of you know the finite difference method. And another is the spherical method. So either of these methods you use and solve this equation, starting from initial condition and solve this equation. That's the basic concept of numerical weather prediction. So this is nothing, there's no magic here. It's all pure science, pure physics, pure mathematics. Okay, and this is the nothing but thermodynamics equation. First law of thermodynamic equation. The J is nothing but a diabatic term, how the radiation is happening in the atmosphere, how the convection is happening, cumulus heating is happening. This is all should be done in mathematical form. It's called diabatic heating. So if you know the initial conditions, you know the forcing force, then you can calculate multiply by delta T, you can get the forecast. So then the model can be integrated to next 24 hours, next model is 48 hours. When you want to really do fast seasonal forecast, you integrate up to the whole season. Then you need more computing time, that's all. But the basic concept is same. So when you go to the seasonal time scale, you need an ocean model also, in addition to atmosphere model. This is the difference. The concepts are same. I'll skip all these things. Then this fellow came, Professor Edward Lawrence. He told that, very important concept. He told that you solve any equation. For example, he solved this equation, these three equations. He tried to solve it with an initial condition. And you start one with the initial condition, get a result. then change, perturb a little bit in the initial condition, very little, and solve this equation again, you will get an entirely different answer. Entirely different. This exactly happens in the atmosphere. So this concept called chaos, you must have heard about the word chaos, CHAOS, chaos. It's a chaotic theory. And so atmosphere is basically chaotic. It depends on, so weather prediction is nothing but the initial value problem. You know the initial conditions, you know the forcing, you can integrate and get the new results, new state. So, but if you don't know the initial state very well, if there are some changes, that can give entirely different results. That's the meaning. And so if you really first start from here and make small changes, you can see how the output is changing. The blue color is going somewhere, red color is going somewhere, green color is some changing. But the initial condition changes are very, very small. And if you really start, this initial conditions are red, and this is the blue initial condition, initial state. After a few days, what will happen means the red will end up here, and blue will end up here. Entirely different state of atmosphere. Okay, and this looks like a butterfly. This looks like a butterfly, isn't it? So this effect is called butterfly effect. That the concept is any physical concept is any changes in occurring in some place, it can have an effect on far away places. It's called butterfly effect. The meaning is the atmosphere is very chaotic. So initial conditions are very important. If you don't fix the initial conditions very well, so if you have better accuracy of initial conditions, forecast also will come correct. Now, important concept, I will tell you that many people, you also may be having feeling, oh, India, we have very poor forecast. When we predict, it doesn't happen. But in America, it happens. That's what main people. I was asked when I was secretary by big people, oh, I went to US yesterday, it was a good forecast. They said it will rain, it rained. But when you say rain, it doesn't rain. I said there are differences in terms of science. The science is this chaotic theory. In the middle latitude where US and Europe is there, the effect of chaos is much less. Whereas in the tropical region, the chaotic influence is much more. So initial conditions are very important. So we cannot really compare apples and oranges. So when somebody says Europe, the forecast is good. But you ask a European man to come here and issue forecast, he'll make the same mistake. He may be making worse bad mistakes than us, because we know our climatology. Well, we know what will happen, but they doesn't know anything. So it is not a question of who is doing it, it's a question of where you are doing. So that, if you really appreciate this concept, I'll be very happy. Okay, good. So this I'll skip. I'll skip. So the question is how weather forecasts are improved. This is the weather forecast, how good forecast for 3 days. Of course, 3-day forecast will be much better than 5-day forecast. 7-day forecast will be much worse than 5-day forecast. When you go on a longer time scale, the forecast accuracy will reduce. But this is an actual observation skill. We started from 1981. You can see in around 2010, the 5-day forecast, somewhere here, the 5-day forecast was as good as 3-day forecast. Similarly, somewhere here, the 7-day forecast here, 7 days forecasts are equivalent to 5-day forecast. So over the year, the accuracy of forecasts have improved substantially. It's all increasing. You see that? Even 10-day forecast is increasing. Somewhere only the 3-day forecast has become a plateau. It is not improving much. It's not much improvement. But whatever science we do, the forecasts are improving in 5 days, 7 days, and 10 days. So substantial improvement is happening. It happens in India also. When we try to do this kind of analysis, monsoon forecast, we found that over the last 10 years, we could improve the forecast by 2 days. It's a substantial achievement. So that means whatever we could predict for 3 days earlier, the same skill we have now for 5-day forecast. Same skill. So there is really a substantial improvement in the skill of the weather forecast. This is I'll give a quiz. These are the 4 photos of the same phenomena, clouds. Out of this, 1 is observation, remaining all 3 are model prediction. Can you guess which one is observation? If you cannot differentiate, that means the models are good. Okay. So this is the actual observations. And you see how the models are predicting so accurately. This is a 9-kilometer model. This is a 9-kilometer model without deep convection. This is 1.4-kilometer model. Almost it's pretty good. You see here and all, the same cloud distribution is well predicted. The models are good. Weather prediction models are good. Okay, so this is the models being used in, and even in India, the weather forecasts are much improved over the years. I'll skip. What is the more important is, in general, the forecasts are good for, it will rain or not. In India, I'm talking about Indian monsoon. But when we predict a heavy rainfall even, when it happens from 65 millimeter, 100 millimeter in a day, the models are not good. So that is very clearly seen here. So this is the distribution of actual observations of different centimeter per day. See, 2.5, then 5. You can, these are lines of forecast. You can say even 2-day forecast, even 5-day forecast, you can see when then the rainfall is less, the models over predicts. It is much more than the actual observation. But when rainfall is more, it under predicts. That means it goes on predicting less and less rainfall, light rainfall, but when it comes of a heavy rainfall even, the model doesn't do well. That's a universal phenomenon. You take any country, the models are too good in moderate to light to moderate rainfall, but when it comes to heavy rainfall, models are not doing well. So, but that is the main concern for all of us, because the heavy rainfall causes flooding. So unless you predict those heavy rainfall events, how will you predict the flooding? Isn't it? So that's a basic question. So, but models have problems. It is improving. I'm not saying it is not improving. Still, we have the concern. This I will skip. This is the forecast for river basins. But tropical cyclone, you must all be watching a tropical cyclone forecast by IMD. Over the years, it has improved substantially. So that's very clearly seen in this forecast. In the average tracker, our forecast is substantially improved. Our forecasts are now pretty good, tropical cyclones. It's a escape. Then when comes out monsoon, monsoon seasonal forecast, monsoon, whether this year will be a drought, this year will be a flood year, or next year will be a normal year. This is a seasonal monsoon forecast in which I worked for almost 25 years. It's a tough job, because you are predicting what will happen for next 4 months in some day. So sometime in the end of May, you say that in June, July, August, September, this will be the total rainfall. So you are predicting much more. And this chaotic theory says that over Indian tropical region, you cannot make a deterministic prediction more than 7 days. In the middle latitude, it could be 10 days. So then question is how you predict on seasonal time scale of next 120 days. So mainly because the seasonal time scale, the rainfall variability is influenced by ocean. Ocean moves very slowly. So if you know how the oceans are behaving, you can predict the seasonal rainfall. Whereas weather prediction is basically atmosphere. It's very highly chaotic. So that's a basic difference. So this is a person who really started good work. He's called Sir Gilbert Walker. He was on the DGM of IMD for many years, 1920s. And he has a big history. He was a big mathematician. And he is the person who nominated C.V. Raman for Nobel Prize. So you can understand how good people are working in IMD at that time. Okay. So initial his forecasts are pretty bad, pretty bad. So me, Salojana Galgil and Navin Anjun analyzed these papers, forecast from 1923 to 80, because the first seasonal forecast was issued on 4th June 1886. India was the first country to start a seasonal forecast in any part of the world. So we are the first country to start. And Walker was one of the responsible persons later years. And so we analyzed this forecast and we tried to analyze, and we found the skill is not that good. Even if you try to understand monsoon better, but those forecasts from 1924, 87, 23 to 87 was not that good. So it is a paper confessing that IMD's forecasts are not good. I was a part of IMD team. I was involved in monsoon seasonal forecasts, but I put my neck out and along with Salojana, wrote a paper and published Current Science. It created a lot of discussion. You may be knowing, forgot his name, Jairam Ramesh, who is the MP, Member of Parliament in Congress. He knew me, he knew Salojana Gargley. He read this paper. He took out the printout of this paper, went to Parliament and told the top 2 scientists in the country saying that your government's monsoon forecasts are not good. Monsoon forecast. So he took this is probably the first time a research paper is taken to the Parliament and got it discussed. So then I was taken back, then I was feeling that some people will ask questions, But the government took it in a defensive way. Yes, our forecasts are not good. So that's why we are spending another 500 crore for IMD. So that was the beginning of IMD's modernization program. So I am very happy. My paper helped IMD to get 500 crores. That's why how science can be used to effectively to help the country. That's a simple example. At the same time, my heartbeats in those days were very high. Okay, good. So then this is the monsoon forecast for recent years. It's pretty good. But monsoon seasonal forecast, I should assume that I should confess that it's not that skillful. Okay, this is a lot. I'll skip. I think I brought a lot of transparency. Then I'll go more to the climate change. When you talk about climate change, it's not prediction, but it is a projections. You must be knowing this book. I don't know how many of you know. This book is published by IITM group. When I was secretary, I asked them to prepare. So this book is available free of cost. Free of cost in the download. You can download it. It's published by Springer. This book shows the national climate change assessment. This is the first time a national climate change assessment was made in the country. So this was a report, and this you can see that. And what the monsoon, future projection of monsoon says that monsoon rainfall will increase. So we'll have, with a global warming, we'll have better monsoon. The quantum of rainfall will increase. But also you should assume the frequency of heavy precipitation, which leads to flooding, also will increase. Okay, and also the number of the length of dry spell, what is happening in the monsoon season also will increase. So we have a critical issues in the coming years, especially is relevant for farmers, saying that you will get good rain, but it will be all in terms of heavier precipitation, followed by a longer dry spell. So that's very important for precipitation. This is escape. And this is the 2018 Kerala floods. I don't know how many of you know. How many of you are from Kerala? I don't know. You know. Okay. 2018 was a flood. There was a film called 2018 flood. It went out to Oscar. He did not get anything. But then there's a paper by British group, Hunt and Aradi. They wrote a paper. If the same weather system, if it occurs in future, it will produce 36% of more heavy precipitation over Kerala. Same precipitation, same weather event. I mean, with the global warming, the effectiveness of a weather system contributing to precipitation will increase more. It will be much more heavy precipitation in the coming years. And also, I did not write here in the paper they written, the capacity of the present dams in Kerala will not be sufficient to take care of the water which flows on those. 2018, there was a controversy that they did not open the dam, so they had floods. But so now they say that when dam will not be sufficient, present dam will not be having enough capacity to store the water if it happens. It's a very, very warning message. And hopefully Kerala government knows about it. How will improve? I think I'll spend another 5-10 minutes. Okay. How will improve? As I said, that weather prediction is nothing but an initial value problem. Okay. So if you have better initial conditions, you can improve better. You can improve weather forecast. The basic problem in the weather prediction is the physics. I told that there's a term called J. J is nothing but diabatic heating in the atmosphere. That is caused by radiation, that's caused by precipitation. I mean, cloud goes, water vapor goes, it gets condensation, so latent heat will be released. So all diabatic terms. So all these physical processes are not well understood, and it is not well represented in the model. The model doesn't really understand the cloud process very well. We know on the laboratory, we know how the cloud process happen. But the real atmosphere, it may be different. It may be occurring in the same physics, may not be different. Because you cannot have different physics in the atmosphere and different physics in the lab. It's all same. But the way of the things interact each other in the cloud, within the cloud, how the droplets grow, etc., may be different depending upon the environmental conditions. Those things are representation that models are not that good. So physics should improve. That's one. Second is you can further improve using AML methods. So I'll give you a couple of slides more and I'll stop here. These are some of good observations which has come out. So we are looking for new innovative methods of observations. Typical surface observation alone will not help. So we need a vertical profile, etc. So this is one satellite. It was launched by Europe. So it can measure the vertical profile of the winds. Very, very useful data. So we are looking for such kind of satellite observations. And then we have different kinds of precipitation. Some precipitation are convective nature. It rains in few hours and goes. Some rains are very steady rain. It rains in few millimeter, but it rains for many hours. It's called stratiform rain. And so these convective rain and stratiform rains are different. In the model, most of the rainfall is convective rain. Stratiform rain, it doesn't really pick up. So that is a basic difference. So when we really have this kind of distribution in the actual observations, the model also should be able to predict, but model doesn't really pick up. So cloud is the cloud. So I will give a statement. Clouds in the models are cloudy. It's a cloudy issue. So unless you resolve the clouds in the model, you cannot improve the weather forecast. So what you need is you need more cloud observations, more experiments with the model, more laboratory experiments, etc. We need for more cloud. And so this I'll skip. So this is a recent paper. It's a very, very controversial paper. They say that, I'll give an example. This is from IPCC models. And this is the actual observations of how rainfall is associated. When El Nino happens, there's a phenomenon called El Nino. When El Nino happens, what will happen to the precipitation? So when El Nino happens, this region will get a lot of rain, but Indonesia and India will get less rain. That's very common. So this is the observation. But in the model, you see the Indonesia, the first model, 2001 model, precipitation is more. When El Nino happens, the Indonesian region and Indian region, they get in more rain. And that signal is not even changed in the latest model. So this is a very serious issue. So if the model have this kind of uncertainty, the model doesn't even pick up the signal of El Nino over Indonesian region, where it's very critical, Indonesian and Southeast Indian region, then how you believe this model? How, and your all policy matters, the discussion of mitigation, net zero emission, COP meeting, UNFCCC meeting, fighting with the US, Japan, you reduce your fossil fuel. But it's all based on your model observation, model forecast, isn't it? Model projections. But this is the problem with the model. So these people have come out with the model so that because once we are not able to, I told the clouds are an important issue. These people say that the basic problem is getting right kind of clouds in the model. The model simulation of clouds is not good. So how you can do is, one is improve the observations, that's one. Second thing is improve the model resolution. At present, IPCC models of the resolution of 150, 200 kilometer. How a cloud? Cloud is of 5 kilometer, 10 kilometer width, and you represent it in a grid size of 200 kilometer. You cannot really truly represent, isn't it? So what we need is, you need model which can resolve clouds. It's called cloud resolving models. At present, we use cloud resolving model for weather prediction for next few hours and next few days. But they are saying that use it for climate change. So that's a very drastic session, very, very drastic session, and it involves huge investment. And so they call 1 kilometer global model. The model resolution should, global model with 1 kilometer resolution. You can just imagine. But they say that it should be done. And I hope these are some examples how the clouds are. We have a lot of cloud observation. One, we have an observatory over Mahabaleshwar, and we are setting up a network over Bombay, already done 4 radars plus some surface observations. We get a lot of rainfall observations there. And we have a lot of aircraft observations for clouds. So we do a lot of measurements on clouds. We spend a lot of money. In 2018 and 19, we did the experiment in over what is that place? District east of Pune, starting from Satara. Satara district. They did this experiment. 2 aircraft we hired from US, and we bought a radar. And we did the experiment. 240 hours of observations, and we spent 200 crores. Very high, very expensive. But we got a lot of good observations. So we do a lot of work on clouds. And this is the 1 kilometer model. They say that if you really do that, you see how beautifully the models are predicting the small distribution of clouds. Very small specks of clouds, it can be predicted. So ultimately, people say that we need to move to 1 kilometer model. We say 1 kilometer model. But from moving from 100 kilometer to K-scale means 1 kilometer, climate model horizontal grids implies order of 2 power 20 times increase in computer power. So huge expense. 22 petaflop of machine cost us 1,000 crore. So you can imagine 20 times, 2 for 20 times computer power if you want to buy, how much money it will be needed. But that's the kind of investment we need for climate forecast. I'll start with the 2 slides. This is the new trend for weather and climate forecast. Google has come up, many companies, Google, NVIDIA, this one company in Penghu in South Korea. At least some 3 companies have come out with a AML model for weather prediction. This model is called WeatherNext. It has come out very recently. So they say it's a Google DeepMind and Google Research produces this model. And they say that they claim that these models are too good. For example, one is the tropical cyclone median track error. This black is for the conventional physical model which we use, we call NWP model. But whereas the GraphCast, the Google forecast, are much less error when compared to, this is the number of days. You can say up the 5th day, the forecast of typical forecast will be having this kilometers error, but this GraphCast will have this much error, so much reduction there. And also you can see the one typical cyclone forecast, 7-day forecast, these actual observations, and how these forecasts are from GraphCast. And they say it takes a single Google Cloud, this is the TPU, they say just 8 minutes to produce 15-day forecast. 8 minutes and 15-day forecast to produce. Whereas in the conventional tradition-based physics-based model takes hours together. So the advantage of AML is much cheaper in computing. So you can do it in few hours, a few minutes, the 15-day forecast. Whereas the physical model will take hours together to make the 15-day forecast. And they claim the forecasts are as good as or better than the physical model forecast. So AML is the new era where people are concentrating on weather and climate forecast. Only problem with this, the AML method doesn't understand why their forecast went bad. If really the forecast goes wrong, you cannot ask AML why it went bad. He will not know. He said, you gave me a wrong data, you produce a wrong forecast. That's all they will say. But in a physical model, you can go inside the model and try to understand what really happened. Because it is all physics-based models. AML only understands the numbers, data. You cannot ask questions to them. If you want to believe, believe, otherwise leave it. Forecast is bad, bad. For a physical model, you can go and ask questions. So there's a lot of conflict of interest among the weather forecasters now, whether you should really follow physical model, which is the investment, I said, 2 power, 10, 20 times of computer power you need. Whereas in AML, you don't need this kind of computing power. So can't you do the same thing? But as a physicist, we may not really interested to do. As a physicist, I will not be interested to do. I'll stop here. Thank you.